Welcome to our webinar on advanced chemistry using KNIME, the RDKit, and Python together. Just a quick note before we start. If you have a question or comment you'd like to make, please use the Q&A section in Zoom to post your question. If you keep an eye on that and you see other questions come in that you'd be interested in seeing have answered, please upvote them there. I'm being joined on this webinar by Elise Krebs. Elise just turned her camera on so you can see her. Elise is going to be paying attention to the Q&A session and we'll be answering questions that can be quickly answered just in text, and the other ones that require longer answers, she will flag up and then will ask me those. She'll interrupt me and ask those questions so we can get them answered. As a reminder, the session is being recorded and is going to be available on YouTube, and we'll send you a follow-up email later today that contains the slides that have all the links, the promo codes for the free book downloads that we'll talk about later, as well as all the downloads. So you'll get an email later today with that information. For people who are not familiar with Zoom, if there's anybody left in 2020 who doesn't know Zoom, if you look in the Zoom window down at the bottom, there's the Q&A box. And if you click on that, you can ask a question there. And as I said, Elise will be monitoring that and will ask me whatever questions come up that she can't quickly answer in text. So let's move on to the content. So we're going to talk about doing advanced chemistry on KNIME, and we're going to do that with the RDKit and Python. The title of this could be done just with emojis or icons, which I kind of like, but this doesn't work well on some social media platforms. So there you go. This is the actual name of the webinar. The goals of this are to show you some advanced tricks for using KNIME, Python, and the RDKit together, some advanced techniques. So we're going to show a couple of things, show you how to use KNIME and Python, also KNIME and Jupyter notebooks. And then throughout all of this, we'll weave the RDKit in so that you can do chemistry. The specific data set that we're going to use today, it's worth mentioning. It's 1,200 compounds that have measured Ki values for CDK2 that were exported from Chemble. I'm going to show you the workflow, actually, that I used to export that to make a point later on. The workflow itself can be downloaded. There's a link here, and either Elise or Sina are going to paste that into the Q&A, into the either Q&A or chat, so that you have this link if you want to download the workflow. If you follow the link, you'll land on the KNIME Hub, and you'll see somewhere on the page something that looks like this, and over on the upper right is this download button. If you click that, you will get a .knar file or a KNAR file. If you have KNIME installed, you can double click on that and it'll open KNIME and install the data, workflows, and notebooks in your KNIME installation so that you can follow along or so that you can use this workflow later. The workflow that I'm going to show you is pretty complicated. We're not going to talk through the whole thing. It does something fairly complicated. It actually does a number of fairly complex things. And in this webinar, we're just going to look at a few of those, mainly the pieces around using KNIME and Python together. So what we're going to do overall in the workflow is read in a set of compounds and data. Those are those CDK2 compounds from Chemble that I talked about. We're going to remove duplicates and subset those compounds, and then do clustering and pick the interesting clusters. We will find the scaffold for each of the clusters using a fuzzy maximum common substructure approach, and then we're going to clean that up a little bit. And when we do that, so to this point, it's all been purely KNIME. When we do that cleanup, we're going to use Python from inside of KNIME, and we'll look at that in detail. Once we've done that, we're going to interactively pick a single cluster and the scaffold that goes along with it. We'll then do an R group decomposition for the compounds that were in that cluster using the scaffold. And then using another bit of Python inside of KNIME, or actually a couple bits of Python inside of KNIME, we're going to enumerate the compounds, the missing compounds based on the scaffold in R group. So compounds that could be formed by attaching the R groups to the scaffold that were not present in the original data set. So that's the overall workflow. Again, you have the whole workflow, you have the data, you have the Python, so you can use this yourself. We're not going to cover all of it in detail. We're just going to focus on some of the Python bits. We're going to be using the RDKit, so for people who don't know that, just a brief introduction to what that is. It's an open source cheminformatics library that's written in C++. You can use it from Python as well as from KNIME, obviously. The KNIME wrappers are maintained by the open source community. The primary maintainer of this is a former colleague of mine at Novartis, Manuel Schwarze. There's a screenshot on the right-hand side that shows some of the RDKit KNIME nodes. The kind of things that you can do with this in KNIME are the typical types of things that you would like to do with molecules and workflows. You can do descriptor calculation, clean up structures, generate canonical smiles and fingerprints, scaffold substructures, many things. And I will talk about some, we're going to talk about some of those and get into details on some of those today. I sent you have a link already to the KNIME Hub. This is just an aside. KNIME is somewhat overwhelming. There's a lot that you can do with it. We have a lot of resources available to help you learn how to use KNIME. But in case those are not adequate or you want to find additional information, the Hub is a great place to do that. You can go and search here and find workflows. You can find particular nodes, KNIME nodes. From those nodes, you can then find workflows that use them. And you can also find extensions and components. And we don't have time to go through all of that today, but it's just a great place to find publicly available workflows using KNIME that you can learn from. The page with some additional resources. We're going to paste a lot of these into either the Q&A or the chat so that you have access to them. The ones I want to emphasize are the life sciences landing page. This is something relatively new on KNIME.com, which is a page that those of us in the life sciences team are maintaining to kind of provide pointers to some of the material that we generate. So it's a good place to occasionally keep an eye on to see what kind of new things we've done. I want to also call attention to the KNIME Press. This is a link to a specific book, the Will They Blend book, but if you go to the KNIME Press, which you can get to from our website, it has access to all of the ebooks that we've produced, and there's a number of them starting with covering KNIME basics up to fairly advanced topics, including things like text mining. We're going to send you a code at the end in the email that you get. We'll send you a download code that'll allow you to access any of those books for free. And that will be valid through the end of the year. And then one last point is the forum. So it may be that if questions come up that are out of scope for this webinar, we point you to the forum. That is an interactive forum where the KNIME employees pay attention to that, but also the open source community pays attention to that and answers questions, provides example workflows, etc. So it's a great resource, again, for help and for learning more information about KNIME. Okay, so let's move on directly to KNIME. Let's get out of PowerPoint and actually look at KNIME. I'm going to start with a very simple workflow. This is not the complicated workflow that goes through all the R group decomposition stuff. I want to say a few things about the way the KNIME Python integration works, and specifically the way that works with the RDKit to kick off. So what this workflow does is something very simple. I'm going to read that file that has the CDK2 data from Campbell in the file reader. That file has a smiles column in it, and I'm going to convert the smiles into, I'm going to convert the smiles into RDKit molecules with this RDKit for molecule node. We can look at the output of that to see what that looks like. So you can see I have a input here that has 1,173 rows. Those are one for each of the molecules and data points, and then 29 columns. And at the very end of this, we have sorry, this is taking a bit the first time it loads. We have the smiles, which are being rendered as structures. If you have the Chemaxon extensions installed, you get a nice rendering of the molecule for smiles. And then there's the RDKit molecule, and you can see the RDKit version of that molecule. So now with this KNIME table, I'm going to show using, I'm going to call Python using this KNIME table, using two different approaches, both with the Python scripting node. The first is some purely Python code in the scripting node, and the second one is going to use Python that's actually in a Jupyter notebook. Let's start with the pure Python. So I double click on this to configure it, and it'll open up the Python scripting node. You can see in the middle, I have my Python script. And on the left-hand side, I have information about the workflow itself. So these are the columns of the data table that are being passed in. These are flow variables that are available. The right-hand side has some information about the Python environment, so variables that are defined in the Python environment. And again, in the middle is my Python script. The important thing to know about the Python node, the Python scripting nodes, is that you get KNIME tables as Panda data frames, and you provide, when you want to provide a table back to KNIME, you provide that back to KNIME as a pandas data frame. So it's pandas in, pandas out at the moment. This Python scripting node is the one-to-one version, so it has one data port as input and one data port as output. So there's one input table, one input data frame, and one output data frame. The data frame that comes in has KNIME types translated to Python types when they can be. Otherwise, they come across as strings. Most numeric types come across without problems. Strings come across without problems. Some things like dates will come across into Python. I believe those come across as strings. And things like if you have a bit vector or a fingerprint in KNIME, that comes into Python as a string as well. So you would, if you wanted to work with that as a bit vector in Python, you have to convert it. But RDKit molecules, when they come from KNIME, show up in Python as RDKit molecules. So if I, in this node, I can do this is a live Python scripting window. Let me walk through what's here, and then I'll do what I'm about to do. So I import some RDKit code. People who've used the RDKit before will recognize some of these imports. What I'm doing in this particular Python script is I'm calculating two descriptors that you cannot calculate from inside of KNIME itself. So KNIME has an RDKit descriptors node that has a lot of the RDKit descriptors, but some, the ones that are specifically the ones that are implemented in Python, you don't have access to in KNIME directly, so you have to do it this way. So the two descriptors that I'm going to calculate inside this node are QED, which is a quantitative estimate of drug likeness. It's a drug likeness descriptor. And then Peter Erdel's SA score, that's a synthetic accessibility measure, so it's a model for synthetic accessibility. And so I want to calculate those two descriptors, both of which you can't normally do in KNIME. So what I do is I start by defining the two lists that are going to hold my calculated values, one for QEDs and one for synthetic accessibilities. And then I loop over the input table, or for each of the rows in one of the columns of the input table. In this case, it's the input table, the molecule column. The way this showed up in here, it's worth demonstrating. I didn't have to type that. I can do for mol in. And then over here, just double click on the column I'm interested in, and it'll insert the relevant text for me. So that's how I got that. And then for each of those molecules, I calculate two values, right? I calculate the QED value, which is in the descriptors module, and then I call the calculate score function in the SA score module. I add those to the two lists. I say that the output table is the same as the input table. I don't need to actually copy it. I'll just assign it directly. And then I add those two columns. This is a pandas data frame. So if I treat the output table like a dictionary and assign a list to it, it'll end up as a separate column in my data frame. So we can see that. I can just here do output table.head. I can execute the script. That'll run the script over the first few rows of the data table, and then put the output to that here down in the bottom. Sorry, I actually have to print that out. So let's try that again. Okay, while this is running, you can see here's the output of that. So there's the first 5 rows. There are 31 columns. Those are the 29 columns we came in with plus the 2 I added. You could also see as I changed that, as I executed that, the contents of the window on the right-hand side changed because I added new modules and new variables. Okay, so that's the basics of using Python from inside of KNIME. Remember, the key points are there's a data frame that comes in, and I have a data frame that goes out. RDKit molecules coming in, if there are RDKit molecules in the KNIME table, I end up with RDKit molecules in the data frame. And if I have RDKit molecules in the data frame going back to KNIME, they end up as RDKit molecules in KNIME. So that's a really convenient way to move those molecules across. That is much more efficient than doing something like converting them into a smiles and then parsing the smiles on both sides. So that's an efficient way of moving information across the two. That only works if you're using a Python environment that has the RDKit installed. So let's quickly talk about that. So the way that you tell KNIME which Python environment to use is in the preferences. And we'll just go to KNIME and scroll down to Python. We really strongly encourage that people use Conda because it makes it much easier to to come up with good reproducible environments. So we provide direct support for Conda inside of KNIME. So you can see here the dialog. I'm using just Python 3, not Python 2, which isn't supported anymore. I did have to tell it where my Conda install was. And in here, I can just pick an environment. So when I open this dialog, it goes and queries my Conda environment to find the list of all of the environments that I have. You can see I have a ton of them. The one I'm using here is Py37 RDKit. So I can pick that, and that Conda environment will then be used for all of the subsequent nodes or all of the Python nodes that I use in KNIME. Okay, I want to also show a script where I use code from a Jupyter notebook because this Python scripting node is super convenient. It's nice just to be able to paste in a little bit of code and try things out. But for me, at least, if it gets more than about this amount of code, more than like 10, 15 lines of code, I find it rather painful to have to do code editing in here, particularly the testing. So I'm much happier working inside of Jupyter. Fortunately, we have a nice way to use that inside of KNIME. Let me show you the notebook that I'm going to be using, and then I'll show you how we use it in KNIME. So I have this notebook called Simple. And in this, I'm going to import do the same thing, basically the same thing we were doing in the scripting node before. So I import the RDKit. I get the assay score ready to use, and then I define a function, return descriptors, that takes a molecule and returns QED and calculate score. So we can try that out. Let's just do, we can see the molecule, and I can then call return descriptors on that molecule. You can see it calls it and it gives me back a 2 tuple with the 2 values. So it's just this is a simple notebook that has a function, and the function takes a molecule and returns those 2 descriptors. So what I want to do is use this code. This is a really stupid example, right? Because this is just way too simple. I'll show a more complicated one later, but just to get the point across, I want to have called this function from inside of my KNIME workflow, and that's in my simple notebook. So let's see how we do that. So in the scripting node, what I do now is I'm going to use this function KNIME Jupyter load notebook. And load notebook takes a couple of different arguments. The 2 that I'm passing to it here are, and for this particular call, is the directory where my notebooks can be found, and then the name of the notebook I want to load. I'm providing the notebook directory using a KNIME URL instead of an explicit path. And the reason I do this is because it allows me to use this workflow on different machines. So as long as I copy the workflow and all of the directories around it somewhere else, this will continue to work, which is why the workflow that I provided you that you can download from the KNIME Hub will actually work for you. So I tell it that the notebooks directory is in the workflow directory, then up one, and then a directory called notebooks. And let's go over here and look in the KNIME Explorer. So this is the notebook or the KNIME workflow that I have open. Sorry, that's not. Let's find the one that I have open. So this is a KNIME pro tip for those of you who don't know it. If you have a workflow open and you want to find it in the KNIME Explorer, you can just click these two arrows in the KNIME Explorer and it'll select the workflow you have open. So that's where I am. I go up one level, so I'm now in this folder. Then I go into the notebooks folder, and you can see in there I have my 3 notebooks, one called Simple, one called Enumerate, and one called Edit Scaffolds. So in the configuration, I point it to that folder, and then I say I want the simple.ipynb, ipynb notebook. And that then becomes this NB notebook object in the scripting node. And now, just as before, I create my empty lists to hold the QEDs and the synthetic accessibilities. I loop over each of the molecules, and for each of the molecules, I call that return descriptors function that's in the notebook. And that returns to me the 2 tuple. We saw the 2 tuple here. The first is the QED score, and the second is the synthetic accessibility score. Returns that 2 tuple. I add those to the lists, and then I edit the output table. And this is a really simple example, so I probably wouldn't in real life use a notebook for something this simple, but I wanted to do the demonstration just using something simple. But this is basically all it does is it imports all the Python code from that notebook, and then you have available all the variables and functions and class definitions, et cetera, that are in the notebook, just in the namespace NB. Okay, those are the basics. Before I move on and get into the workflow, are there questions?
Yeah, we had a really good question. Can we use different Python environments and different Python nodes, but within the same workflow?
Yes, you can. So this is another one of those pro tips. You can use a flow variable, define a flow variable that points to the environment that you want. And then provide that flow variable to the Python scripting node and select it here in the Python 3 command. So that's the flow variable that controls the environment. So you can have a different environment for each of the Python scripting nodes, and you're not stuck using the default.
Otherwise, we're good.
Otherwise, we're good? Okay, cool. Good. So let's look at the main data set, or the main workflow. So this is that giant clustering and R group decomposition workflow. Again, I'm not going to get into details of all of the individual steps of this, but what we do is we read the data in, we cluster the data based on some fingerprints, we interactively pick the cluster threshold that determines the number of clusters. I just show you what this looks like. We're not actually going to do this though. Again, you have the workflow and you can do all these things yourself. So I'm going to, here in this node, I can, this is my cluster tree, and by moving the bar around, I can change which clusters are selected. By selecting a cluster, I can display compounds down at the bottom and see the compounds that are in a particular cluster. So this is an interactive widget for exploring that cluster tree and deciding how many inherent clusters you think there are in the data set and how many you want to take forward. There's a bit more interaction in here to allow you to pick interesting clusters. And then for each of the clusters, we're going to go in and find the core, so the scaffold for the cluster. We're going to do that by finding the maximum common substructure of the compounds in the cluster. So let me show you what the data look like. And this is the same data set we had before. We've now filtered it down, so there's only 233 rows. This data set has, at the end, a column which is the cluster assignment. So every compound is assigned to one of the a cluster. And what we're going to do is find the MCS for each of those clusters. The RDKit KNIME integration has a nice thing that you can do where, together with the group by node, in the group by node, I can say I want to group by clusters. And then I want to count the number of rows in each cluster. So I'm just going to count the number of compound chemical IDs. And then for the molecule column, I want to find the maximum common substructure. So that means for each of the clusters, find the maximum common substructure and add that to the output. There's one more thing we have to do in order to get what we want, and I'll show you that in a second, but let me show you what the output of this node looks like. So there were 6 clusters in the data set. Here's for each of the clusters is the count. So the first one had 26 rows in it. The next one had 16. This one has 25. And then there's a column that has the smarts, which is a query language that defines the maximum common substructure. I will expand this so that you can see these. They're not super informative because there's a lot of query features in here. So it looks really super noisy. I'll show later how we can actually see what these an interesting way of looking at these scaffolds. But these are guesses at what the scaffold might be for each of the clusters. The important thing that we need to do in order for this to actually work is we're going to do a fuzzy maximum common substructure instead of a real maximum common substructure. We have some in previous webinars or trainings we've talked about how to do this. I'm not going to get into the detail, but if you're doing that in the group by node, it is important that you change the preferences for how the MCS is calculated in order for this to work. So I do that again. I go to preferences. I'm going to type MCS in the search box, and what I've done is the preferences for MCS aggregation. I've set things up to do a fuzzy MCS. And the way I'm defining that here is the maximum common substructure doesn't have to hit all the molecules. It only has to hit 80%. I only want ring atoms to match ring atoms. I only want complete rings to match. And in this particular case, I am using the identity of the atoms. I don't always do this. So in some fuzzy MCS applications, you want to allow, for example, carbons to match nitrogens, and you can do that by using compare any. But in this case, we're doing compare elements. So it actually is a normal MCS there. The fuzzy bit is that you only have to match 80%. So at least what I told you before the webinar was wrong, obviously. So you should probably update your settings. Anyway, so in order to reproduce, in order to have the workflow that I gave it to you executed up to this node. So you have, if you're looking at this, you already have that calculation done. But if you want to repeat it yourself, you need to update the preferences in order to do that. Once I've done that, I add the core information back onto the table, do the highlighting of the cluster cores. We can look at those. So what I've done inside the meta node that you can't see, I have generated a rendering of the molecule that has the scaffold for each molecule highlighted. So you can see here, I have a couple molecules. These are sharing the same scaffold. These are sorted by cluster, actually. So as I move down, you can see the same cluster, the same scaffold is showing up. They're not all drawn the same way. I'll show you how to do that later. But initially, we have just all the clusters there, or all the scaffolds shown. We're going to do an R group decomposition with this. And if you've done computational R group decomposition before, you may have noticed that there's something ugly about this, which is there's an atom in the scaffold, this one in particular. There's an atom that is part of a ring. And if I do MCS using this as a core, if I do R group decomposition with this as a core, things are going to be messy because this atom has 2 attachment points to it. So this will be labeled, for example, R1, and this will be labeled R2. And that just makes the analysis really, really messy. So what I want to do is go through each of the scaffolds. And if I have an atom like this, where there's a single atom in a ring, that's part of the MCS, I want to remove that from the core definition so that I stop the core at this nitrogen atom so that this whole thing is an R group instead of having 2 different R groups attached to that atom. Okay, so let's look at how to do that. This would be theoretically possible. So there's no KNIME node, RDKit KNIME node that allows you to do that. You could theoretically do it with the KNIME. KNIME has a Java scripting node where you can script in Java. You could make these edits there if you're comfortable with Java. I'm not, it makes me crazy. So I'm much happier using Python. So I'm doing this with the Python node. Let's look at that node. The first thing you may notice is that I'm loading code from a notebook again. So this is more complicated code, so I have it in a notebook. We'll look at the notebook in a minute. Actually, let's go ahead and look at it. So I'm loading code from a notebook. And then once the code is in, I am going to collect the new cores. I'm going to collect the, let's look at the output of this, and then I'll talk about what the script is doing, and then we'll go look at the notebook. So there are 3 new columns added: mol reg no, an output table that has 3 columns in it, mol reg no, which is just the key for the molecule, the new core definition, and then which cluster it's in. Let's look at that output quickly. See, there's the mol reg no, here's the new core, and there's the cluster that it's in. We join this back on the original table so that we have the new core added to the input table. So basically, this does some work to modify each of the cores, and then the joiner puts it back on. Let's look at the Jupyter code that is doing the modification, and then we'll come back and see how we're using it. So that is this edit scaffolds notebook. You see this one's a little bit more involved. The first thing, what I'm doing here is reasonably complicated. This is actually the part that does the work. What I'm doing here is reasonably complicated, so I wanted to have some testing data. I start by doing the usual set of imports, and then I wanted to be able to test what I was doing, so I start with a sampled core definition that I pulled from an earlier run of the workflow. So this is one of those cores that are in the data set. And then this is just a set of smiles for clusters based on that core, again, that I pulled from the data set in KNIME. For people who don't know how to do that, I got this list of smiles out of a KNIME table by just looking at one of the output tables. Here I have a smiles column. I can select a number of rows in the smiles column. So I select the first one I want to pick, and then go down to the last one I want to pick. Select that too. So now all of them are selected, and then just copy, so Control C. And now what I have on the clipboard is those smile strings. So what I did is just paste that into a Python string and then split it apart based on using the carriage return, and that gives me a list of smiles. So it's a simple way to get data from KNIME to Python for my testing examples. So what I do is I read the sample scaffold in from smarts. I construct the test molecules by converting each of them from smiles. I go through and identify only the molecules in the test set that match the smarts. So this is just a Python list comprehension. This is normal RDKit in Python. So I want each of the molecules in that list of molecules if it has a substructure match to the scaffold. I print out the number that matched. So in this particular case, all 20 matched. And then I'd like to render the things in Jupyter, again, with the highlighting done. And this last 2 bits of code just show how to do that. You have the notebook, so you don't need to worry about taking notes on that. So you can try this out yourself. So they're the first, those 20 molecules with the core highlighted. This is the bit of Python that actually does the work. And what you will notice here is this cell has been tagged. So I added a tag for that export. What I'm going to do on the KNIME side is I have all of this testing code in the Jupyter notebook. And then I have a function. When I bring this into KNIME, I don't want to execute the testing code. I don't need all of that work done, right? Every time I run the Python scripting node, I really only want this function imported. So what I've done, and I'll show you how I did this when we go back to KNIME, what I did is when I imported this notebook, I said only import the cells from the notebook that are tagged export. If you don't know how to tag cells in Jupyter, in the view menu, you turn on the cell toolbar to allow you to do tags. And then you get this extra information. So probably when you run Jupyter, you don't have this add tag thing, and you may not have the toolbar visible at all. But if you've done that, you can then, you have this add tag and you can tag your cells. So this is a trick that I use continuously when I'm using Jupyter together with KNIME. I have lots of testing codes that I can see that my notebook is actually doing what I want it to do. And then the functions and classes that I want access to in KNIME, I just make sure that they're nicely self-contained in cells, and then tag those cells export. So down at the bottom, I then show how to actually, I actually run that prune scaffold command. So I give it a scaffold and it gives me back a smarts. And here I'm showing the smarts mapped onto molecules. So remember, the problem with this particular scaffold is that it's matching these ring atoms. So that the single ring atom is included in the scaffold definition, and we don't want that. And you can see in the new scaffold definition, those ring atoms have been removed. So the R groups will start and include this entire ring. So that's what it's doing. That's the Jupyter notebook. We have the testing code, so I can see what's there. I can make sure everything works the way I want. And then when I import this into KNIME, I'm just bringing across this export cell. Let me show you how that works. So if we look in the Python scripting node, I brought the notebook in the same way I brought it in before. So I give it the notebook directory, I bring in the notebook name, and then I say only include tag export. And so this tells it if there's a cell in there that doesn't have the export tag, just ignore it. So then we bring that in, and now I'm just looping over the input table. So I'm looping over the 2 columns. One is the cluster column and the other is the smarts column. I construct a molecule, RDKit molecule from the smarts, and then I call that prune scaffold function in the notebook. The resulting smarts that comes out is added to this new cores list. I'm sorry, the new cores dictionary. Are there questions about this aspect of using Jupyter or what I've done so far?
We have a number of questions, mostly concerning the Jupyter notebooks or Python in general. So the first one was how to solve the indifferent kernel problem.
I assume that the person has opened a notebook, one of my saved notebooks, and they got a message about it being used with a different kernel that can't be found. Is that what the question is? So if that is the question, when you get that warning, it allows you to pick a kernel that you actually have installed, and you can just pick it and save it. That kernel, sorry, that environment that you're using will have to have the RDKit installed. So what I'm doing here, I'm really careful when I do this. I use the same Conda environment to run Jupyter in that I'm using inside of KNIME. So I have that Pi37 conda environment, the Pi37 RDKit conda environment, and I'm running Jupyter. This is the window that I launched Jupyter from. You can see I activated that Pi37 RDKit environment before I ran Jupyter.
Then another one, is there any loss of performance running Python scripts inside KNIME?
So yes, there is. At the moment in particular, there is a serialization step, so that Java types have to be converted into Python types and the pandas data frames constructed, both on input and on output. So there is a performance impact of doing that. And because very important thing is because we're using pandas, all of the data has to go into memory. Right? Pandas is an in-memory data thing. So if you have a data table that has 1 million rows, unless you have a ton of memory in your machine, this trick will not work. In a future version of KNIME, hopefully the next version, but this isn't done yet, but in a future version of KNIME, we're adding a feature that allows that overhead to go away and will allow you to interact with the data without actually having to load it all into memory first. But at the moment, it is important to know there's bit of performance attached to starting Python the first time and a bit of performance attached with that serialization, deserialization. You'll only notice it if you put this inside of a loop or if you have a lot of rows in your data set.
And another very good question that I'm not sure if you maybe wanted to have it spared for the end. What's the merit to use RDKit under KNIME and not Jupyter? Why KNIME?
Yes, I have a thing on that at the end. That's a great question. And I have an answer. I have what I think is a good answer for that. Everybody needs to make the decision on their own. But I will get to that at the end.
Okay, there are a number of more questions coming up. Maybe this one is fitting at this point. Is there any way to draw molecules of which the MCS is depicted in the same orientation?
Yep, let's do that because this workflow does that. So let me go ahead and this does not. Okay, sorry, I thought this had done that. Do I have one? Yes. Let me show you that, and then I'll show you how we did it. Let me make sure. Oh, that's not generating the images. Oh, yeah, that is okay. Output column. Let's look at the output of this. So the molecule column here, this is a great example because it shows it and also shows one of the challenges with doing this. The molecule column here has the core. It's not highlighted at the moment, but it has the core always drawn in the same orientation. So the core here is, let's see, we have a molecule somewhere with the core highlighted. The core here is the two 6-member rings and then this 5-6 fusion. I mean, you can see in all of these molecules, those are drawn the same way. This is a challenging thing to do because sometimes you make it hard for the code that generates the coordinates to generate reasonable coordinates of the molecule, but most of these just end up looking somewhat ugly, but they're not horrible. But you can see they're all oriented the same way. The way I did that is there's the RDKit generate coordinates node, and I've told that to generate 2D coordinates. This takes an optional parameter, which is the template smarts. And the template smarts is used to identify the core, and it generates coordinates for that core and then matches the core onto each of the molecules and uses those as fixed coordinates. In this particular case, you can't see the template smarts because it's being provided by a flow variable. So that's here. We have a flow variable that is the core of the molecule. But that's the general way to get 2D molecules that are aligned to a common core. In a future version of the nodes, hopefully the next version, but again, not sure because it's not done yet, future version of the nodes, this will take a optional input port, so you can actually provide molecules that have pre-generated coordinates instead of having to just give it a smarts where it generates the coordinates itself, because that way you could then actually choose what the orientation of the core you want is, and it would use that, but that's not there yet. Elise, other questions?
There are. Again, a bit more Python related. Does only include tag option can handle several tags or just one? So it's about the tagging.
Yeah,
I raised a few questions.
Don't remember the answer to that question. I think it can do more than one. Let's just try it. So I'm going to define a silly function, and let's see. So this won't work at first because I haven't imported the silly tag is not being imported. So let's see if I provide this with a list of tags, if it'll work. I'm going to try a couple different things because since I don't remember the answer. I think I asked Marcel to do this, but okay, nope. So it may, yeah, it looks like there may be a way to do it, but I'm not doing it correctly. So I guess the answer to the question is, I don't know, we will get back to you. Yeah, okay.
Then maybe another quick one. Is it possible to use the last version of pandas?
You mean the most recent version of pandas? I don't know the answer to that question. So the KNIME nodes, in order to have the integration between KNIME and Python work, do place some requirements on the pandas version. Pandas, particularly in the early days, very frequently when they released a new version, they would break old code. And because we're making fairly detailed use of it, or fairly in-depth use of pandas in the backend in order to do this translation, whenever they changed the API, it would break the KNIME Python integration. So there is definitely the KNIME Python integration requires a particular version or a set of versions of pandas, and I'm not sure if we have managed to catch up to the most recent one. Things have changed now because pandas, the API has stabilized. So it may be easier for us to remove that, but I haven't tried it recently.
And another one, but I think it's not related to the workflow, so I don't know what your plan is for the last 10 minutes. If you want to proceed, and if we still have time, I would propose we catch up with these questions.
Okay, let's do that. Let's proceed. Okay, so that was another Python node. The next steps of the workflow, we pick the final set of clusters. Then we do an R group decomposition. And let me show you what the output of that looks like. The R group decomposition takes the core for that scaffold. You saw already the generating the aligned coordinates. And then for each molecule, we identify the actual core itself. So in this explicit core column, this has, in addition to the core itself, it also has the R groups labeled. As you can see, this is R1, R2, R3, R4, R5, R6, and R7. And then there's a column that has an RDKit molecule, an RDKit molecule column for each of the R groups. So for each of the 7 R groups. Molecules that don't have a substituent there will have an H added. What we then want to do is enumerate missing compounds, or is enumerate all possible compounds with those R groups. So the first thing we're going to do is go through that table and find all of the members of each, all possible values of R1, all possible values of R2, all possible values of R3, etc., and then put those all together in the one output table that has all possible combinations. There is almost certainly a way to do this with KNIME nodes combined with JavaScripting, but again, I spent a while trying to figure out how to do it and then gave up because I knew I could do it in Python really easily. Let's look at the Python scripting node. It's not super complicated. What I do is I go through each of the R columns and I convert the molecules into smiles and collect those smiles. So for each column, I collect all of the smiles. I convert those smiles into a set, so I have just the unique ones. And then I append that to the overall list of sidechains. So at the end of going through this point, I have a sidechains list that has one entry in it for each of the R groups, each of the possible R groups. And then each of those entries is a set of the R groups that are the actual specific R groups that appeared in that R for that R. So each of the specific smiles. And then Python in the iter tools, if people don't know iter tools, anytime you have this thing, I need to do bunches of combinations or combinatorial explosions or things like that, you always want to use iter tools. So iter tools has this wonderful product function that does the combinatorial explosion I want to do. So that's a nice one-liner. I do that. Iter tools actually gives you a generator object. And it doesn't do the explosion itself, which is good because it can be really huge. I have a hard-coded maximum number of products that I want to provide from this, so I hard code that to 100,000. And then I just loop through each of those combinations, generate a smiles that just has a dot between each of the R smiles there, and then that goes in my output table. So let's look at what that looks like. You can see this is not actually doing chemistry, it's just string manipulation, so it goes super fast. The only chemistry that's being done, sorry, there is chemistry. The only chemistry that's being done is converting the molecules to smiles. You can see what comes out are these list of dot separated smiles where each of the R groups is there and is labeled with the, a dummy atom with the corresponding R group. There's then a Python script, again, using a Jupyter notebook that actually takes the specific scaffold and those R groups and puts them, attaches them, and actually makes a molecule out of it. And for the purposes of the demo, I've put a row filter on top so that this only gets done for a subset of the data. Because what comes out of this is actually 100,000 rows, and doing this with 100,000 molecules takes longer than I wanted to wait. So I just narrow that down to the first 5,000. This Python scripting node is using code in a Jupyter notebook that actually builds those molecules back together. So it creates new molecules inside of Jupyter. And still for the 5,000, it takes a little bit of time, so it'll run those. Then the molecules that come out, we generate the canonical smiles for them. We remove duplicates because you can end up with duplicates. And then using a reference row filter and the canonical smiles from the input table, we remove anything that was present already. So anything that was on the input table that's also in that output table we remove, so we now just have the new molecules left at the end. So let's go ahead and do that, and I'll show you what the output is, and then we will wrap up. So now I have a table with 3,000 rows. These are molecules that could have been constructed from the R groups that were present, but that were not present in the data. This is reasonably, it's somewhat fragile. So you can see sometimes it fails, right? Sometimes it builds a molecule that the RDKit just won't accept. So you don't always get successful molecules out. But this is just a nice way to see what could have been in that data set and wasn't. That's in terms of the overall workflow. Good. So this is the workflow. We've seen a lot of stuff in Python. My next bit is just going to show, to spend a minute or two talking about when you might want to use KNIME instead of Python or Python instead of KNIME, or why you don't want to just be in Jupyter the whole time. But if there are questions about the workflow to this point, I'll go ahead and answer them, one or two, and then I'll do that, and we can come back to the last of the questions because we're about out of time.
There's another quick question concerning the workflow.
Mm-hmm.
Are the R groups reattached randomly or only at the original positions?
Only at the original positions. So R1s, the things from the R1 list only get attached at R1.
Yeah, I think otherwise we're done at this point.
Okay, so let me quickly go to my slide with when you might want to use each tool. These are just my rules of thumb, and they're not comprehensive, so your mileage may vary. The absolute no-brainer for me for when I would want to use KNIME instead of Python is if I'm constructing a complex database query. So this is the KNIME workflow that constructs the KNIME query used to get the data set that we worked with. There are 5 tables in this. There are multiple joins and a bunch of different row filters. Row filter is a where query in the resulting SQL. I could construct this SQL in Jupyter, but it would take forever. And this is just much, much easier to do in KNIME, and it's much easier for me to change it and for me to see how it goes along the way. So building complex database queries, I more or less always do in KNIME. If I want to do interactive data analysis, Jupyter is good at a lot of things, but flexible interactive data analysis is not one of them. It's getting better there, but it's still got a long way to go. So this, having something where I have a nice parallel coordinates plot where I'm filtering on multiple columns and I can see the molecules below, this takes 30 seconds to put together in KNIME. And even thinking about doing this in Jupyter, these two things talk to each other, right? So when I change selection here, it changes what's visible on the table. That is really not trivial to do in Jupyter. So kind of interactive data analysis is another thing where KNIME definitely wins. If I'm doing complex scripting, this is the reattaching workflow. The reattaching script. I cannot imagine trying to implement this in KNIME. So with basic KNIME nodes, you couldn't do it. Doing it with a JavaScripting node inside of KNIME is basically the same as using Python. So I would do this in Python all the time, and I would do it in a Jupyter notebook and then use that from inside of KNIME for the reasons that I talked about before, that it's just clearer where the code is, and I can have the testing code around it, and it just works better. So the nice thing is I gave you some reasons for how I choose between them, but you don't actually have to choose because they all work together really easily, right? So I can use my Python. If I have a Python package that I use regularly, I can use that inside of the scripting node by just importing it. And if I have a notebook, I can just point KNIME at the notebook and use the code from that, and it's not a problem. So that for me is the nice take-home message at the end, is I can use both tools seamlessly together, more or less seamlessly together, and get the best of both worlds. So that's it for me. If there are additional questions, I'm happy to answer them.
We're a bit over time, so I don't know if we can proceed. They're not directly related to your workflow. The first one would be how to render
Sorry. But I'll answer. I mean, I can go for a few more minutes. It's no problem. In case other people have things they need to do. Thank you for attending. I hope this was useful. You're going to get an email that has links to the downloads if you want to watch this again, as well as to the workflows and all of the supporting material and the book codes. You can download books. If you have follow-up questions, please use the KNIME forum, ideally the RDKit section in the KNIME forum, and then I will hopefully see those. I'm not as good at paying attention as I should be, but I'm trying to be better, and there are people who remind me when I forget. But basically, thank you for joining. I hope it was useful. And pay attention to the our social media channel and the KNIME webpage to see when we do the next one of these. So thanks for anybody who needs to leave now, and I can hang out, or I think Elise, if you have time, we can hang out for a bit longer and answer some more questions.
I'm fine, yeah. So if you want to continue with some questions that are not directly related to the workflow, there's another one. Can you show the rendering from E3FP to RDKit? I don't know if that's maybe exceeding totally the scope of today, but
I didn't understand the beginning. The rendering from what? E3FP? Sorry.
The rendering from E3FP to RDKit. That's a question.
I don't understand.
I can't give you more background on that.
I don't understand the question, so maybe whoever asked the question can just clarify in the Q&A, and then we'll come back to it. And if we don't end up coming back to it, ask in the KNIME forum, and we'll get there.
Another one, maybe in the meanwhile to continue. Does including your input data tables in KNIME have an impact on speed, or is it mostly done for organization record keeping over just calling files externally?
Oh, so I think the question is, so I sent you a workflow with everything saved with the data preloaded. And that's a nice reproducibility thing, right? Because you have all of the data together there with the workflow. You can reset the workflow and then the data's not there, and then it'll go on and pull the files in again. So there is a reason to include, you can include the data. It's a nice, you get this nice package where you have the operations on the data plus the data itself. And it's also then more efficient because you don't have to repeat the processing. But you can always just reset the workflow and then the data's not with it. Right? Did that, hopefully that was an actual answer to the question. Hopefully I understood it correctly. But if not, again, please ask the clarifying question and we'll get to it.
And the very last one, not perfectly directly related, but is it possible to bind web framework Django to KNIME like you did with Jupyter? I have no clue on that.
So you can call web services. That's no problem. So if you're using Django and you are creating web services with it, you can connect to the Django the REST-based web services from Django and access that using either the KNIME Python nodes, or the easiest way is KNIME has nodes for calling REST services. So that would be the easiest way to operate on that. In terms of actually importing code from a Django instance, you could certainly, I'm not sure, because I don't know enough about how to do that. If you have a Django instance running somewhere, whether you can get code directly from that. It's been too long since I used Django to be able to answer that directly. Sorry.
Other than that, I think we're clear. If one of the answers was not clear enough or you have further questions, I can also, again, just emphasize the forum, because then we also have more time to go and dig into the answer. So to make sure you will actually get an answer.
Yep. Good. So again, thanks to everyone for joining. I hope it was useful. And again, pay attention to our social media feeds and the KNIME webpage, because we certainly will do something like this again at some point in the future. Thanks, everyone.